All right, shall we get started? So I graded Lab 7 yesterday. I apologize, I thought I'd get it done the day before, but I didn't make it. And so I generally try to get these back the day they're due, because I think students profit from seeing the answer and seeing what they did wrong right away. And I hope that you're paying attention to what the autograder, it's not, output from the autograder isn't great, but it does show you, it does give you some insight as to where you went wrong. And I hope that you're paying attention to that. Question day 12, which is due just before class, I'll get to tonight, and you should have it by late tonight or early tomorrow morning. I'm going to give you a question of the day at 11 o'clock today. It'll come out. You'll detect a theme. There's the questions of the day's specifications are getting less specific. They're becoming more informal, and you'll notice that question of day 13 is related to question of day 12, and question of day 14 will be related to question of day 13. So I'm trying to, with the series of questions of the day, focus on list manipulations of the kinds we're doing with sorting and searching, especially with sorting. That means destructive list operations. And there's a sort of an emphasis on iteration, not as comprehensions and not necessarily as recursion. So you'll see that in today's question of the day. Homework 2 will be coming out next week. I think you'll enjoy it. I've got a prototype implementation. It's kind of cool, I think. So it should be fun. And I want to remind you of the correction I made in class. The one colons were missing in the slide last week, or last Wednesday. So this is the actual solution to int alt sum from last time. Okay, questions? All right, so question of day 12, which was due today, inversion index, which takes a list or sequence of unique orderable items. So sequence, obviously they're orderable, but I put orderable in to remind you what that means. Unique means that we don't have to worry about multiple copies of the same element. Think deck of cards, not random numbers that might repeat. And computes what this made-up index we call the inversion index, which was defined as the number of inversions as you scan the sequence, the number of times an element that is larger than another element occurs before that other element. So the number of exchanges you would see as you scan. So the idea here is to scan through the list, counting the number of inversions you see, and you're going to have to essentially scan every element and compare it against every other element. Now the key insight here then is that I'm going to have to use two loops. One that scans from the very first element up to but not including the last element. So as I scan through the list, I stop short. And the other index that starts one beyond where I am and scans to the rest of the list. So I'll always be comparing an element in the list before with an element of the list afterwards. So let the first element be every element in the list except the last one, and compare that element with every element that comes after it, counting how many times these things are out of order. That's all you have to do. So we count these. As I scan, so I starts at the beginning and stops too short of the end. J starts one beyond I and stops right at the end. One short of the end and stops right at the end. And so if I, which is the element before, the lower index element, if Li is greater than Lj, so if the value found at the lower index is greater than the value found at the higher index, that's the very definition of inversion. Then add 1 to the inversion counter, which I neglected to initialize here, but I did in the solution. Nuts. I'm missing an inv equals 0 at the top. I literally wrote this slide like 3 minutes ago, and then I ran over here, and it's like, I hate it when I do things in a hurry. You may notice I've been making a lot of mistakes on slides. I feel badly when that happens, but I want you to know we're hiring faculty in the CS department. And so I spent much of the day yesterday on the phone, actually on Zoom, with 2 candidates that we're trying to attract here. And it's really quite stressful because they, you guys probably don't know this, but faculty candidates, you go through this search process, right? We invited 10 candidates to virtual campus to give day-long interviews. Two of them pulled out of the search along the way because they got offers from other schools. This is a really competitive market for CS faculty. Some schools are hiring 10, 20, 30 faculty. We're hiring 2, so it's quite competitive. And they want to talk about every little thing. So I'm gonna rant for a minute. It's not just salary. They always want more salary, but it's like, I would like to have $100,000 a year to spend on whatever equipment I like. And it's like, well, I don't have $100,000 a year for each of you to spend on whatever you like. I don't know where you think I'm going to get that money. So it's stuff like that, and it's quite stressful, and I apologize for not being fully in the moment here. But there is an inv equals 0 missing there. Okay, so that's what's missing. But the idea is clear. You scan, you let one pointer scan the list, and the other one start wherever that one is and scan the rest of the list, and you make those comparisons all the time. And whenever they're out of order, you add one to the inverse. Yes, and the question in the back. No, this is I is the lower index. So left to right, I comes from the starts at the left, and j is the index beyond it. And you only count an inversion if the value at I is actually bigger than the value of j. The expectation is that the value later in the list will be bigger. When it violates that expectation, you add 1. Okay? Everybody okay with this? So then I just counted, and then there was this formula I gave you. And the formula is nothing more than a way to normalize the value, the number of counts, against the length of the list, so that if the list is in order, the inversion index will be 0. And if the list is inverted, then the inversion index will be 1. That's all. Just scales everything so that you go from 0 to 1. Yes? It says L of I what? Less than L of j. Did I do that on the specs? Yes. Holy smokes. All right, well then you can do whatever you want and count something, and you'll get credit. Man, I can't believe I did that. I had the specs backwards. God, bless America. Now I got to go check question of day 13, make sure I didn't mess that one up. Question of day 13 is a whole lot of random, though, so almost anything goes, so I'm probably okay. All right, well, this is the solution I had intended. Does everybody sort of get the idea? I'm sorry I made it not make much sense to you if I had it backwards. But the idea was to scan and count inversions. And when you have the number of inversions, you divide that by the number of comparisons you can make, which is this formula here. And that gives you this sliding scale from 0 to 1. Now, why do I care about this inversion index? Let's talk a little bit about the function I gave you called scramble. Remember scramble from, I forget what homework? It was also reproduced in this inversion index thing. Scramble is actually the Fisher-Yates shuffle algorithm. It's an algorithm that takes a list and produces what's called a fair shuffle. So a fair shuffle is a shuffle that takes the elements and shuffles them up so that every permutation is equally likely. That's a hard thing, right? That's a hard criteria to meet. But it's a very elegant algorithm, runs from right to left, and it ensures that you have equal opportunity to get any of the possible n factorial permutations available to you for a list of length n. All right? You can test that. You can take that scramble algorithm and do it 1,000,000 times on a short list and count how many times each possible permutation comes up, and you'll see that it's roughly uniform, which is what you want. Now, in question of day 13, you're going to implement an alternative shuffle algorithm, which is not fair. And I wanted to have a way of comparing the output of the scramble algorithm, which is the fair algorithm, with the output of your question of the day 13 algorithm, which is not a fair algorithm. And just to sort of explore these kinds of measures that we can use on algorithmic operation, on how well the algorithm works, how expensive it is, and so on. So that's why I introduced the inversion index, and that's why you're going to be doing question of the day 13 the way you are going to be doing it. And I will check the specs. I apologize. God, can't believe I did that. So here's the correct inversion index running on Scramble, and you can see that we don't know where L is a list of, again, that should be range 10. God, I'm not having a good day. Where when I scramble this list L, I'm going to have, when I scramble L, I'm going to get some random permutation, and I would expect that on average, the inversion index should be right about a half. Because if I'm doing a fair shuffle, on average, I should expect to have the elements, roughly half of them out of order. In other words, half the comparisons to be wrong. So that was what I was hoping to get to, but I totally bollocksed it. Oh well. Let's go back to sorting. This is a little bit more secure. So last time we talked about selection sort. Remember selection sort? Scan and replace. The idea was to find the smallest element of the list that remains. So I'm going to, starting at element I, consider the rest of the list. I'm going to find the minimum element in the rest of the list, and I'm going to find its index. Now remember, we're assuming, not necessarily the case, but for now we're assuming that these are unique elements in the list. So think deck of cards again. And so I will find the first occurrence of this element, which is the only occurrence of this element, because there's only one of each. Find the occurrence of the minimum element, and that will tell me the smallest element. Then I need to swap the two elements, the smallest element with the ith element, and this gives me my selection sort algorithm. Let's look at the way it works. So I will be the index starting at 0 and going up to the length of L minus 1, because we stop one short. The last element is by definition sorted. And what I do here is I search from I, which is initially 0, so the entire list. I search for the index of the smallest element. Where is the smallest element of L? And when I find that, I set j to be whatever offset I have plus what this returns, because the index here is returned relative to the starting element I. And if I want the index to be relative to the entire list, I have to add that I back in. So j now is the location of the smallest element, and I can swap the ith element and the jth element. I can invert them with that simultaneous assignment, and that's my selection sort. So to see this, we're just going to do a quick selection sort, if I can get this to show me the right thing. Sometimes it just is useful just to do this by hand, right? So you can see what's going on. So here are my elements. So I goes from 0 up to, but not including the last element. So I'll start here. And what I want to do is I want to scan the list for the smallest element, which is this one. I want to exchange this one with the ith element, so I'll swap those two. Now I want to advance my pointer so I becomes 1. I look for the smallest element here, which is this one. I want to exchange it with the ith element, but it's already there, so I exchange it with itself, which does nothing. I advance my pointer. I look for the smallest element, which is that one. I exchange it with this element to get this list. I advance the pointer last time through because I stop one short. I scan the list for the smallest element, which is that one. I do the exchange, and I'm done, and the list is sorted. Does everybody understand that mechanically? Yes?
So what happens if you, for the range?
What happens if I what?
For the range, what happens if you just do, the range is the length of L?
So what if I went one more instead of stopping short? Well, the question there is, it's actually an interesting question, but let's just do that. Let's advance the pointer and ask myself, what's the minimum element in a list of length 1? It's always the element that's there. So nothing will happen, but I'll do extra work that can't make any change. Right? For a list of length 1, we know a couple of things. Any list of length 1 is automatically sorted. Right? Not in order, so it's in order. The value, the minimum value of a list of length 1 is the only element in L. The maximum value in a list of length 1 is the only element of L. The min equals the max, and it's sorted. So I don't need to do that last pass simply because there can be no good reason to do it. Okay? Is everybody good with this? So that's our selection sort algorithm. And you'll remember that, by the way, I don't think that was captured on video. I couldn't get it to take the doc cam, so I apologize for those watching at home. You'll always wonder what we were doing. We were sorting cards. All right, so that explains the selection sort algorithm. Is everybody okay with that? The question I had for this is, how fast does it run? And we had asked ourselves a better question of how does it behave as the length of the list grows. So here is the size of my list, how big n is, and I just measured the runtime of selection sort. I took a list of that many elements, I randomly scrambled it using the Fisher-Yates algorithm, which you know as scramble, and then I sorted it and I timed the time, and you can see that the runtime grows with this sort of upward-facing curve. This is a characteristic quadratic curve, so it grows as n squared. So the bigger n is, the amount of time it takes grows as n squared. Now, come on. Really? You're going to stop working? Man, I'm just going to pieces today. So not only could I time that function, which is what I did for the previous graph, but I could also count how many times I make comparisons between two numbers. Right? So if I look at the selection sort, if I look at selection sort, where does a comparison occur? Well, it's inside here, where I'm looking for the minimum number, the smallest value in this list. How many comparisons do I make? If I have a list of 100 elements, think how you would find the minimum element, how you would do it without using just min. How does min do it? Well, the answer is simple. You start at the first element. You say, let's take that first element as being the minimum. And I'm going to compare that with every other element. And when I encounter a smaller one, I'll remember the smaller one. When I encounter the larger one, I'll still remember the previous one. So I'm going to do a scan and look for the smallest element. So if I have a list of n numbers, and finding the smallest number will take about n comparisons. We're going to have to compare that number, a number, with every other number. It's actually n minus 1 comparisons. So in that comparison thing here, I'm doing roughly n amount of work. So if I were to count those comparisons that I make, since I'm doing n amount of work every time through a loop that runs n times, you can see where that quadratic behavior comes. And in fact here, with n at 1,000, here I've got 5 times 10 to the 7th, 5 times 10 to the 7th comparisons. You can see that it just runs up. It has exactly the same shape. So comparisons are a useful proxy for runtime. So what have we done? We've implemented our sorting algorithm. We've timed it on random lists. We've seen that it has quadratic behavior. And the observation that I make here, which is really important, foundational observation, is that instead of timing something, I could just count how many times some fundamental operation occurs in the algorithm. And here, for sorting, the fundamental operation I choose is comparison. Right? So how many comparisons does a sorting algorithm make? That helps me predict the runtime of the algorithm. It tells me not how fast it will run, but it tells me how it will scale as n gets larger, which is the thing we're after. The question is, can I do this? Can I come up with an estimate of this behavior without writing any code? That's the purpose of the lecture today. And the answer is yes. So the way we do this is we're going to skip doing all this implementation and timing and testing, and instead we're going to estimate this runtime. It's called an order of estimate. We're going to do this with this back of the envelope kind of algebra that I'm going to show you. So we're going to look at the code, which can just be a sketch of the code. It doesn't have to be actually written as if you could execute it. It could be pseudocode. It could be an English description of the code. And I'm going to identify that fundamental operation in that description, and I'm going to ask myself, for an input of size n, how many times am I going to do that fundamental operation? If I can come up with a description of the number of fundamental operations in terms of the size of the input, well then I'll know how to predict the runtime of the algorithm. That's the insight of what we're after. Is that clear? Any questions? So I'm going to look at the description of my code. I'm going to find the fundamental operation. I'm going to derive an expression that tells me how many times that fundamental operation is executed as a function of the size of the input, and then I'm going to call it a day. So this is the third way. We're not going to do any timing. We're not going to write code and then actually keep a counter of how many operations we do. We're going to look at the pseudocode description. So pseudocode is something that looks like code but actually won't run on your machine. Now, no jokes about having written pseudocode in class because my code didn't run today. But the idea is it's an English description of how the code might work. When I showed you the sorting algorithm with the cards, you might write down an English description, start with the first card, scan the rest of the list. It's that kind of description. Call that pseudocode. And then we're going to derive this estimate with this little back of the envelope kind of reasoning. So we're going to do a very simple approach to this. You will find, as you go on to discrete structures and data structures in next semester, you'll do more of this. When you get to algorithms, this is what algorithms is all about, so you spend a lot of time on this analysis. But the one fundamental thing to think about this analysis is that it is an estimate of how the program's runtime grows with the size of the input. That's the first thing, which we've already discussed. The second thing to know about it is that it's a worst case estimate. So what does that mean? Well, we just saw selection sort with the cards. Let's look at it again, and let me ask you about the runtime of selection sort the second time. Let's do this in terms of comparisons. What if this were my input list, just the way it is? How much work would I have to do? The answer is I would never have to exchange anything because it's already in order. So this, in a sense, is the best case for a sorting algorithm. If I give you a list that's already sorted, then you're going to do very little work. Sure, you might do a bunch of comparisons, but you'll never have to make any exchanges. In algorithmic analysis, we're going to explicitly focus not on the best case, but on the worst case. In other words, how many operations do I do if everything goes wrong? If every comparison says you got to do some more work? If every step of the algorithm where there's a path through the algorithm where you do less work and a path through the algorithm where you do more work, you always take the more work path. So that's the key insight we're going to have to follow. Secondly, order of analysis ignores any factors that are not dependent on n. What does that mean? Let's say I have an algorithm that runs 10 times faster than another algorithm. Both algorithms operate with this quadratic relationship on input size. So I have an order n squared algorithm that is 10 times slower than the other algorithm, but they both vary in runtime in accordance with the square of the input size. Well, in order of analysis, those two algorithms are exactly the same. We can't distinguish them. A factor of 10 difference does not depend on the input size, so it's ignored. The only thing we care about is the rate of growth of runtime over the size of the input. If the algorithm is proportionately slower, but proportionally to a constant factor, meaning that it's just a fixed number of times slower or faster than another algorithm, those two algorithms are indistinguishable. So only factors that depend on n matter. So this measure that we're going to derive is really coarse, and it only really holds as n gets very large. So you've all had calculus or are about to have calculus, or maybe are in calculus. In a sense, this runtime analysis works in the limit. As n gets very large, this algorithm will always be faster than that algorithm. That's the kind of reasoning we're after. Finally, these are presented, order of analysis has results that are presented in what's called big O notation. So this algorithm that is order 1 means that it runs at the same speed regardless of the size of the input. What's an example of a constant time algorithm or an order 1 algorithm? An algorithm that chooses at random a card in a deck. No matter how long the deck is, how many cards are in the deck, choosing a card at random will take exactly the same amount of time. That's an order 1 algorithm. What about order log n? This is an algorithm whose runtime grows slower than the size of n. We've seen one algorithm that's log n. Who remembers what it is? Anybody? Binary search. Binary search runs faster than the size of n because we compared binary search with the serial scan search, which was order n, and log n is always less than n. What about an n log n algorithm? Well, we haven't seen any of these yet, but we will. Probably not today, but certainly on Monday. But we've certainly seen an order n squared algorithm, just saw selection sort. Finally, you can imagine an order n cubed or n to the 4th, and then you get to this kind of algorithm where the n is in the exponent. These algorithms are called exponential time algorithms. We can go beyond that. There are even slower algorithms. But an exponential time algorithm is important in computer science because this algorithm is an algorithm that runs in exponential time is infeasible for problems of realistic size. All right? So classic problems that run in exponential time are very, very hard problems that are not always solvable in real world. Now notice none of this addresses whether the algorithm terminates and whether the algorithm returns the correct solution. We assume that it does, because if it doesn't terminate, doesn't return the correct solution, it's not useful. So the algorithm has to be correct and terminate. And once we know it's correct and terminates, the question is, where does it fit on this hierarchy of runtimes? And if I have two algorithms that are both correct and both terminate, and one is here and the other one is here, well, the answer is always pick the faster one. That's what we're after here, right? So I just showed you selection sort. I can show you insertion sort, bubble sort, all sorts of sorts. They're all going to be here, except that one of the sorts we're going to look at is going to be here. So which sort do you pick? Well, you pick the n log n sort over the order n squared sort. Every time. Okay? So let's see what this order of analysis is. So we're going to look at an algorithm. I'm going to show you algorithms in Python because it's the language we share, but they don't have to be in Python. They don't have to be in a real programming language. They can just be English sketches of an algorithm. That's fine. And we're going to look at the written representation and we're going to apply these 5 rules. The first rule is called direct sequencing. It says the cost of executing operations in sequence. So I have a sequence of steps. The cost of executing those operations in sequence is the same as the cost of the maximum cost of any one of those operations. So I have a bunch of operations that take one time step, and then one that takes order n squared time. The cost of all of those together is just order n squared. This embodies that worst case assumption. All right? So the order of a sequence of steps A, B, C is just the same as the maximum of order A, of order B, of order C. First rule. Second rule, conditional execution. The cost of executing a conditional expression, if condition, then something, is the maximum cost of evaluating the condition and the expression. So in an if, let's just take an if statement that's simple. If condition, do something. Else, do something else, perhaps? So if condition, do something, else do something else. Well, it is the maximum of the cost of the condition evaluation and doing sequence 1 and doing sequence 2. In other words, you have 2 paths through this conditional statement. If the condition is true, you'll do sequence 1. If the condition is false, you'll do sequence 2. This simply says pick the most expensive one. So this is kind of a natural sequitur to this first rule, right? In the first rule, you have 3 things to do. The cost is the worst of the 3. In the second rule, you're going to do either these 2 things or these 2 things, and it says pick the worst, the cost of the worst. Okay? So that's rule 2. Rule 3, iteration. Let's think of our classic for loop. The cost of executing a for loop is the product of the cost of what's going on inside the loop times the number of times you run through the loop. So a for loop of something that takes order n time If it's executed n times, if the loop loops n times, that cost will be n squared. But if the loop always runs 3 times, and the internal part is order n, it's still an order n loop, because the 3 doesn't depend on the n. So in short, a loop k times the sequence will be order of k times the sequence. But if k is independent of n, then it's a factor we can just drop. Remember, constant factors go away. We're not interested in actual dominating runtimes. We're interested in how the runtime functions as a feature of n. That means that something that looks like order 10n and order 3n, they're both just order n. The 10s and the 3s go away, doesn't matter. So 3 rules so far. Sequential execution is the worst time. Conditional execution is the time of the worst path. And iterative execution is number of iterations times the cost of the internal part of the loop. If k is independent of n, you just forget about it. Okay, rule 4. Now it gets a little bit more complicated. Rule 4 has to do with invoking a function. So in Python, you write a function like np in the last lab, and you use it in another function like rqp. The cost of invoking that function is the same as the runtime of that function itself. So you analyze the runtime of function np, and whenever you see an np in your pseudocode, you add in that runtime of that function. And finally, rule 5, recursive execution. The cost of a recursive function invocation is the number of times that that function is invoked times the cost of the non-recursive part of the function. This is complicated. You'll see it in an example, will make it easier. So those are my 5 simple rules, and I'm sticking to it. It's not great, but this is a CS1 level understanding of order of analysis. Let's take a look at a pseudocode description of selection sort. Now, one of the things you'll notice, this thing here looks a lot like my selection sort from before. You'll notice that this is really not legal Python, right? This isn't Python. It's pseudo Python. There's colons missing. Sure, there's some stuff that looks familiar, but and we're using indentation. But you know, like even the expression here is done differently. It's not the range. It's just written differently. It's just so that we remember what the generic idea is. It's not intended to execute. It's just for us to examine and sort of immediately understand. So here's my selection sort. It looks just like the one before. I'm going to let I range from 0 to length of L minus 1, inclusive here, because I think that way. I'm going to find the minimum value in the tail, ith tail of L, and then I'm going to exchange. And this find min thing, instead of using all the built-in list expressions and the slicing like I did before, I wrote it out. Here's find min. I set the index to 0. I scan the list from 1 to length L. And if Li, which is initially L0, is less than L index, then index is I. So L index starts out as 0. So I compare each element to L0. And whenever an element is less than L0, I replace index with a pointer to that element. So this is that scan and look for the lowest element thing. And then at the end of the day, I return I. So this find min finds the minimum index in L. The index of the minimum value in L. Does everybody understand this? It's just like the selection sort we did with the cards, just like the selection sort we saw in Python. Now, what I want to do here, I notice that n is the length of L. I'm going to decide that the size of the input, of course, is the length of this list L. And that varies each time I invoke the problem. Short list, long list, doesn't matter. So n is my currency. I want to know how fast this algorithm runs with respect to n. And we use our own implementation of find min rather than the built-in L.index because I want to be able to look at these things more closely. All right, so I'm going to start with find min because remember, rule 4 tells me if I have an invocation of find min, I need to first know how fast find min is. So I'm going to start with find min, and I'm going to label over here in the corner, this is a simple expression. This is a fundamental thing. It's an assignment. It does not depend, the cost of doing this assignment does not depend on the length of L. Every time I just assign a number to a variable, it costs me one, think of it as one operation. So I'm going to label this one order 1. And inside the loop, the condition and the index assignment here, these are both order 1 operations. And just for convenience, the return, which just simply returns from the function, that's a constant time operation. None of these lines of code here, or none of these operations here, depend on the length of L. L can be 1,000,000 elements, and the cost of assigning x to 0 is going to be the same. Doesn't matter how long L is. So these are all order 1 by rule, by identifying the constant time operations. Now, I'm going to look at this loop in here, and I'm going to apply rule 2 that says the cost of this entire loop here, sorry, I'm looking inside the loop. This is rule 2, which is for conditional expressions. The cost of this conditional expression is the maximum cost of the expression that is the condition times the cost of the body itself, which is only one operation. Since both of these are order 1, the maximum of order 1 and order 1 is simply order 1. Okay? So this little block of code here is itself order 1 by rule 2. This piece of code and this piece of code have not changed. So I'm just going to reproduce them over the right so these things line up. So I have order 1, order 1, order 1. I haven't accounted for this loop, which I have to do next. So rule 3 tells me that the cost of this whole loop here is however many times I run the loop times the cost of what's inside. Well, I notice that this loop I ranges from 1 to length L, which is size of length 1 to length L is exactly how many elements I have in L. So this is going to repeat the loop n times, actually n minus 1 times. Close enough. N minus 1 times the internal cost of this is n times order 1, which is order n. Now notice, I didn't make a fine point here about n and n minus 1. Why? Because like multiplying n by a constant, adding 1 or 2 to n doesn't change n. Think of it this way. As n gets large enough, whether you're at 999,999 or whether you're at 1,000,000 isn't going to matter. Right? It's the sort of an order of says, look at the dominating factor. The dominating factor here is the size of the list. If the list is big enough, keeping track of all the minus 1s, plus 1s isn't going to change anything. So don't bother. So now I have, this is still order 1. This whole block here now is considered order n. The last return is order 1. I have 3 things that occur in sequence. The cost of find min then is the maximal cost of those 3 elements, which by rule 1 is just order n. So this little analysis done on paper tells me that finding the minimum value will cost you n amount of work for a list of length n. Now I'm ready to sort of start in on selection sort here. So I'm going to do the same thing here. I'm going to identify that min equals find min by the rule that says that the cost of a function invocation is the runtime of the function. I'm just going to pencil in an order n here. The cost of an exchange here is 2 assignments really, contemporaneously, but that's still order 1. Now, that leaves me with just trying to figure out how many times this loop runs. But before we go there, I want to point something out. This find min is order n only if the argument itself is of length n. And you'll notice that here, this argument starts out when I is 0, this L is in fact of length n. But as I gets bigger, the size of the argument I'm passing to find min gets smaller. You see that? So the first time through it's 10, then it's 9, then 8, then 7, and all the way down. But in order of analysis, because I'm interested in the worst case, the way to handle this is to say, how big can this be? And the answer is, the biggest it's going to be is order n. And just use the largest size. Now, as just a little mental digression here, What if I didn't do that? What if I counted 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4? What if I did all that work and kept track of those? How many times, what would be the total size of the list on average? Well, the answer is an average of a collection of numbers from 1 to n. The average value is n over 2, which is 1/2 times n. But guess what? 1/2 is a constant, so I just drop it in my order of analysis, and I get the order n I'm after. So there are two reasons to see an algorithm that's called on a list that's progressively shorter. It makes sense just to start with the maximum length of the list and use that as the size of the input to that function. Everybody follow that? Okay. So by rule 1, this is order n. This is a sequence, order n, order 1. Rule 1 says take the maximum. The body of this loop is order n. By rule 3, this I goes from 0 to length of L minus 1. That's n minus 1. It's close enough. That's order n. So order n times order n gives me order n times n, which is order n squared. So even our little back-of-the-envelope analysis, which didn't require that we implement any code, didn't require that we time it, that we test it on sample tests, that we run many test cases so we got good average run times, didn't require us to instrument the code and count conditions or anything like that. It just required a few minutes of pencil and paper analysis, literally like on the back of a piece of scratch paper, tells us that selection sort is order n squared. We make n minus 1 passes through the data, just like our cards. We had 5 cards, we made 4 passes. On each pass, we compare the remaining n minus 1 unordered elements, which in the worst case cost me n work. I swap the smallest element with the lowest location that's still under consideration. That is a constant time operation. So as n gets larger, I make about n passes of, on average, n over 2 comparisons, which makes for order n squared behavior. This is the short text that goes with that painful back-of-the-envelope calculation we did before. And it is just as good a comparison, just as good an analysis of what the expected runtime of selection sort is than having to implement it and test it. So at this point, you should be convinced of one thing. We've implemented selection sort. We've tested it by timing it on sample inputs. We've tested it by counting conditions as a fundamental operation on sample inputs. We've analyzed it using these 5 analytic rules for order of analysis. And in every case, it is order n squared. So you should be thoroughly convinced that selection sort is order n squared. And the next question is, are there algorithms that do better? So once you have a mechanism to analyze an algorithm, this order of analysis, the next obvious question is, can I say something fundamental about the problem rather than about the algorithm? In other words, so far we've managed to use order of analysis to say, this problem requires, this solution runs in order n squared time. But we don't settle the problem for good. It's conceivable that if you think hard enough, you'll find a sorting algorithm that operates in order n time. I haven't said anything about that. I've said selection sort is order n squared. I can promise you that insertion sort and bubble sort, they're all order n squared. But it leaves open the possibility that if I think hard enough, I will find an order n times algorithm to do sorting. And that would be good, right? Better to be faster. Always better to be faster. Well, the answer to this is that you always have that uncertainty about whether a better algorithm exists unless you can do even more sophisticated reasoning. And that more sophisticated reasoning isn't about reasoning about a prospective algorithm. It backs up one more in the design stage and says, let's just look at the problem. Forget about the algorithm to solve the problem. I don't know what it should be. Let's just look at the problem and see if I can make a logical argument that says this problem, no matter what algorithm you use to solve it, will require at least this much work. So think what that means. It's really a powerful idea, because if I can look at sorting in the abstract and say, hey, I don't care how you sort this list, you are going to have to do at least n squared amount of work in this little algebra to guarantee that that list is sorted. Forget about how I can do that. There are ways of doing it. Let's say I say to you, hey, sorting is going to take order n squared work, no matter how you do it. That's what it's going to take. Think of what that means. That means once you have selection sort and you've decided it's order n squared, you know for certain that you can stop looking. You've done the best you can possibly do. There is no algorithm that runs better because you've shown that any algorithm that solves this problem uses at least n squared work. So it sort of closes a circle. I have an algorithm. I've analyzed the algorithm. It requires this much runtime. I've analyzed the problem. It requires at least the same amount of runtime. I've closed the gap between my implementation and the problem. I have the optimal solution. Now, computer scientists love optimal things, right? Engineers in general, we love optimal things, right? I mean, how many of you go to the grocery store and try to reason about the queuing line, which line is the best line, right? How many do that? Let's see a show of hands. It's got to be the majority of you, right? That's why you're here. If I did this in Victorian literature class, everybody would be going like, I don't know, any line will do. But you guys actually think about it. You say, well, there's 4 people in that line and their carts look pretty full. So that's an order n squared operation. And over here, I've got 4 people in the line, but they only have 1 item. So that's an order n operation. You do this all the time without thinking about it. Computer scientists love to do this. They love to say, assuming that every checker works at the same rate, I have the optimal line. My engineering daughter, when I travel with her, the thing that sets her off, because she's a little bit particular, the things that sets her off are the TSA lines, right? Because the queuing configuration of TSA lines can be really badly done in most cases, right? They're like, or God forbid, customs line. They're multi-server, multi-queue solutions. So she will rant and rave about the optimal configuration of these lines. If you think like that, then you'll take to order of analysis in just the right way. So if you don't normally think like that, try to adopt that mindset because it'll help you. Now, I can tell you, just to make a long story short, sorting is not an order n squared problem. It's an order n log n problem. So we still have an efficiency gap. I'll tell you that the analysis of sorting says you must do at least order n log n work, whereas the analysis of selection sort shows us that's order n squared. So there is a better sorting algorithm, which I will show you next time in class. Now I want to show you one last thing here today. Do we have time? We have 3 minutes. There's this cool, kind of cheesy, but also kind of cool website. This is a group in, I think they're in Slovenia. And they had another website that's not. Here's an example, backtracking ballet, 10-year anniversary. Okay, we'll do binary search. So can you see this? No. So this is a group of computer scientists, in part. And what they do is they dance different algorithms. This sounds really cheesy, but this is the flamenco version of binary search, which you all know, right? And you notice that this person has a 7 on their back, and we're assuming that the list is ordered 7. It's only is much better with sound. I don't know why I'm not getting sound. So she goes to the center element. You do a little dance. Sometimes better to do this faster. They do their little dance, and she will flip around, and you will see her number on her back, and that will help us rule out half the binary search. You'll notice that they're showing you the pointer here. Okay, 5 and 7. So what does that mean? In binary search, that means that the value 7 must lie on the right-hand side of this of this queue. So we rule out the left-hand side to reveal that they're sorted, but they're sort of out of the search. So now she will flamenco her way to the center red dress. You get the idea. Well, you can find selection sort, insertion sort, binary sort. And the cool thing is every one of them is a different dance type. So you'll see like the folk dance version of selection sort. These are generally much better when they're run faster. So yeah, they have a different, oh, geez. They keep changing their website. They do have a Facebook group. But if you just search for it, and I believe the website index I gave you is good, it's kind of entertaining and you might enjoy that. And see if you can understand the behavior as it goes. Ask yourself if it's order n or order n squared. All right, we'll see you on Monday. Have a good weekend.